So Unit 2 deals with basic algebra and measurement conversions. Coming up in a week or so, we'll start doing the measurement conversions. Today we want to look at our basic algebra and the rules of algebraic numbers and some problem solving so that we can build up to some of the medical applications next week. So we have algebraic numbers that behave exactly like the other types of numbers we've talked about so far. An algebraic number, as we saw in the first day of class, might be a 4x. And just like every other number we've worked with, it has two parts. The 4 is a count that tells us how many. We have 4 of something. And the x is a name that tells us of what. Just like having 4 inches, 4 cows, even 4/7. And it behaves just like any other number. Remember our rules when we add or subtract. We must have the same name. And we keep the same name. So for our algebraic numbers, that looks like this. If we have 4x plus 9x, we have the same name, x and x. We're going to combine the counts. 4 plus 9 gives us 13, and we keep the same name of x. If I have something like 5x plus 2y, the result's going to be what? Trick question. It's just going to be 5x plus 2y. We can't combine those with addition because they have different names. Now for multiplication and division, remember we do not need the same name. And when we multiply or divide, we also combine the names. So if I have my 4x times 9x, what do I get as a result for that? Heard somebody whispering it there. 36, and what for the variable? X squared, very good. Because when we multiply, we combine the counts. This time we're multiplying, so we combine them with multiplications. 4 times 9 does make 36, but we also combine the names. So x times x gives us the x squared. And if we have 5x times 2y, what are we going to get? I heard there 10xy. Very good. Because we combine the counts. 5 times 2 is 10. And we also combine the names. X times y is just xy. So as we look at combining items with algebraic numbers, we might have something that looks like this. 7x minus 3y plus 5x plus 8y. When we look at that, we see that there are different names, and we're adding and subtracting. However, if we look more closely, we see that there are some that are the same. We have 7x. What can we combine that with? The 5x. And now when we're dealing with something like this, the operation here goes with the number that comes after it. So this plus here is saying that's a positive 5x. So 7x and positive 5x make 12x. Now for the y's, that looks like a 3y, but remember the operation in front of it goes with the number behind it. That subtracting 3y means that that has to be treated as a negative 3y. So it's a negative 3y and a positive 8y. Negative 3 and positive 8 give us positive 5y. Now we have to have an operation in here to connect those. So since that's a positive 5y, we put plus in here. Okay, so we want to look at now adding more complex algebraic numbers. And I want to show you some similarities between our algebraic numbers, what you've referred to most likely as polynomials, and our standard whole numbers. If we look at our place values for whole numbers, we had ones, tens, hundreds, 1,000s, 10,000s, 100,000s, and so on. Well, from what we know about powers, this is 10 to the 0. Anything to the power of 0 is 1. This is 10 to the power of 1, or just 10. 10 squared, or 10 to the power of 2 is 100. 10 to the third to get the 1,000. 10 to the fourth to get 10,000, and so on. And we looked at taking numbers like 3,472 and writing them out in their full form, or what's sometimes called expanded form. We said that is 3,000s and 4 hundreds and 7 tens and 2 ones. But with what we just wrote up here for our place values, instead of writing out the words thousands, hundreds, tens, and ones, we can just write it like this. 3 times 10 to the third is thousands, plus 4 times 10 to the second is hundreds, plus 7 times, we just put 10 for tens, and plus 2, and 10 to the 0 is just 1, so we're just going to leave that as a 2 there. And when we write it out like this, with our 4 digits all written out in expanded form, we can now start to look at how the structure of algebraic numbers is similar to that. Many of you have probably seen an algebraic number that looks something like this. If we look at that, this is 5 times x to the third, 7 times x squared, 2 times x, and then 8 times is ones, or if you thought about it as x to the 0. You see here, these x's now become the place values instead of the tens. Instead of 10 to the third, it's x to the third is our place value. So 10 squared, it's x squared. Ones are still ones because 10 to the 0 and x to the 0 both equal 1. So when we go to work with these polynomials, the operations with polynomials, even though we've been taught several shortcuts for working with them, we can actually go back and do them just like we do with whole numbers. So if we have 3x squared plus 7x plus 11, we're going to add to that 2x squared plus 5x plus 7. First thing you'll notice that's a little bit different, not only because the algebraic numbers have to be written out in full form or expanded form, you'll also see that within a single digit we can have, within a single place value you can have more than one digit. We don't have to carry over. We can have an 11 in there in that ones place. So anyway, when we go to add, we'll take our 3x squared plus 7x plus 11. And we're going to line up our second number so that the place values line up. So the 2x squared goes under the 3x squared. The 5x goes under the 7x. And the 7 goes under the 11. And we are now adding down those columns. And we can treat this just like whole numbers. 11 plus 7 is 18. It's positive, so we put a plus in front of it. 7x plus 5x is 12x. It's positive, so put a plus in front of it. 3x squared plus 3x squared plus 2x squared is 5x squared. Now that one being at front, it's positive. We don't need to put a symbol there. So we get 5x squared plus 12x plus 18. Now a lot of you have been taught for adding polynomials, just drop the parentheses and combine like terms. That works just fine. But this is really the long way, the real way of adding polynomials without the shortcuts. Now I purposely made every digit positive here. It's a little more difficult when we start throwing in negatives. And that is another one of the differences between these algebraic numbers and whole numbers. If I have negative 238, that's a negative 200s and a negative 3 10s and a negative 8 1s. But in an algebraic number, each digit can be positive or negative on its own. Whereas in these integers, either every digit's positive or every digit's negative. So I can have 5x squared minus 9x plus 2, where the 5x squared and the two ones are both positive, and that 9x is negative. So I'm going to add that to negative 3x squared plus 7x minus 13. It's still going to be the same process. I set it up, lining up my place values. So the negative 3x squared goes under the 5x squared. The positive 7x goes underneath the negative 9x. And the negative 13 ones goes under the positive 2 ones. And we are still adding our columns. Now remember, when I'm dealing with negatives, I kind of keep a picture in my head. So 2 plus negative 13 ends up being what? Somebody be brave. 2 plus negative 13. Go positive 2, back the other way 13 spots. We end up at negative 11. Very good. Negative 9x plus 7x. So negative 9 plus 7 is going to end up at negative 2, and of course it's 2x. Now since those are both negative, I didn't have to put a symbol in because we already had the minus sign there. 5x squared plus negative 3x squared is, where do we end up at? 2x squared. Very good. So the addition isn't really that much more difficult with the negatives. Subtraction is where the negatives really kind of cause some issues. Now I'm going to start out with this first one, being all positive digits. The results may not all be positive, but it's going to start out the same way. 3x squared plus 7x plus 2. We line up, that's supposed to be an x squared there. Line up the 5x squared with the 3x squared, the 3x with the 7x, and the 4 with the 2. This time, however, we are subtracting down the columns. Now, most of you are probably taught just to distribute the negative, they call it. So change the sign of every number in the second one and then drop the parentheses and combine like terms. But what's really happening is what we're doing right here. What is 2 minus 4? Negative 2, good. 7x minus 3x. Negative 4x, good. And 3x squared minus 5x squared? Negative 2x squared. So even though all the results came out to be negative there, the fact that all the digits were positive in the original numbers made that one not so bad. It's when we get into things like this that it gets a little scary. So 5x squared minus 11x plus 5 minus 3x squared plus 7x minus 4. So we'll set this up. Put the 3x squared under the 5x squared, the 7x under the negative 11x, and the negative 4 under the 5. And we are subtracting down our columns. Now when I do these, I like to write them off to the side so that I can deal with the subtraction. I'm going to slide this over just a little bit. Give myself some room. So here we've got 5 minus a negative 4. 5 minus a negative 4 is going to become 5 plus 4. So that is just positive 9. Good. Here we've got negative 11x minus 7x. So negative 11 minus 7, which is going to become negative 11 plus a negative 7. So negative 11, negative 7 becomes negative. They go in the same direction, so the 11 and 7 combine to make 18. Perfect. Negative 18x. 5x squared minus 3x squared. (2x squared). Wonderful. So you can see this process is the same as adding or subtracting whole numbers. It's just you have to deal with those negative digits. Like I said, most of you are probably taught to just do this, distribute the negative. So this becomes plus, this will become minus, this becomes minus, that becomes plus. So it changes the sign of every digit in the second number, and then you combine like terms. 5 and negative 3 make 2. Negative 11 and negative 7 make negative 18. 5 and 4 make positive 9. If that's the way you're taught, please feel free to keep doing it that way. That's just fine. Now, we've already seen multiplying the single-digit numbers, like 7x times 5x, where we combine the counts. 7 and 5 make 35. And x times x is x squared. Just like when we're multiplying any other number. If I have something like 3 times 42, if I were going to write that out, I would do it long way. It'd be 42 times 3. I always put the number with the most digits on top. And then we have to multiply out. 3 times 2 is 6. 3 times 4 is the 12. Same process is going to go for our algebraic numbers. I might have 5x times 3x minus 2. We can set it up exactly the same way. We have 3x minus 2 times 5x. And I can do 5x times negative 2 is negative 10x. Negative 5x times 3x. 5 times 3 is 15. X times x is x squared. That again, that's the long way, the real way of multiplying that out. Now, most of you have been taught a shortcut called distributing. If you multiply this using distribution, what you've been taught is first, you need to look at the parentheses and make sure there's nothing you can do inside of those parentheses. In this case, there isn't. That parentheses is not an enclosing symbol. It's not telling you to do something there first. It's just a separator. It's just keeping the 3x minus 2 as a single number. So there's nothing to do in the parentheses, so we have to do something to the parentheses. And that's times the 5x. So to distribute, you would just do 5x times 3x, which is 15x squared. And then 5x times negative 2, negative 10x. So you can see we get the same result. This way is, like I said, that's the real way of multiplying it out. This is a shortcut, and as you can see, it saves a lot of space and a little bit of time. So for this class, most of the time, I'm going to do it this way just to save the time. What if we have 3x minus 5 times 2x plus 4? Now again, I'm going to show you a way that's different than what you've seen. The real way, the long way to multiply this out is just like multiplying out any other number. We put the two numbers one above each other. We start out with the last digit of the bottom number. 4 times negative 5 is negative 20. 4 times 3x is 12x. So we've multiplied everything in the top number by the 4. We move over to the 2x. Just like before, we put in a 0 down here before we move over. 2x times negative 5 is negative 10x. So that putting in that 0 keeps the x's lined up. 2x times 3x is 6x squared. And now we can add our columns, add them up. We got negative 20, 12 and negative 10 is a positive 2x, and 6x squared. That is the long form of multiplying out two polynomials. Most of you have been taught a process called FOIL. What does the F in FOIL stand for? First, right? So that means I multiply the 3x and the 2x to get 6x squared. What's the O stand for? Outside. So it's the outside two digits. 3x times 4 makes positive 12x. The I stands for inside. Negative 5 times 2x is negative 10x. Then the L? Class. So negative 5 times 4 is negative 20. And then we have to come back and combine the digits that are like terms. So the 6x squared doesn't change. 12 and negative 10 make positive 2x minus 20. So we get the same answer. This is just quicker and saves a little space. Now, one of the things I don't like about FOIL is it's being a gimmick. If you run into something like this, 2x plus 7 times 3x squared minus 8x plus 1. Now that there's a middle digit here, FOIL doesn't work. It becomes FOIMAMOIL. But if you did it out the long way, it's still just the same process. You just put the 3x squared minus 8x plus 1 on top, 2x plus 7 on bottom, and you multiply it out. Now, I do realize if you're using a FOIL, you just modify it so that you do 1, 2, 3, 1, 2, 3, and add the like terms. Okay, seems like you guys are pretty good with your operations with algebraic numbers. For the division side, the only thing I'm going to show you is simply this. If I have 12x and I'm going to divide by 6, I can combine the counts. 12 divided by 6 is 2, and nothing has happened to the name, so the x stays there. If I have 24x squared divided by 8x, I can divide the counts. 24 divided by 8 is 3. X squared divided by x is x. Or I might have 32x squared divided by 4x squared. 32 divided by 4 is 8. X squared divided by x squared cancels out, so it's just 8. Okay, so what is it that we want to do with all these algebraic numbers? Realistically, there's not a lot of practical applications of just combining the algebraic numbers. They become more practical when we look at problem solving with them. And to do that, we have to look at a structure like this. X equals 5. Of course, that's called an equation. And the way it operates depends on this symbol here, the equal sign. Now, the equal sign, if I ask people to define it, it's often, they find it difficult to define it without using the word equals. So if we look at it, the equal sign means what's on one side has exactly the same value as what's on the other side. In fact, you can think of it like a balanced scale. What's on the one side exactly balances what's on the other side. So you look at it like that. Now, all equations start out like this, as a variable equals a number. And they're built up from there. To build them up, we can do any of our basic operations. We can add, subtract, multiply, divide, and we can even do powers and roots, logarithms and exponentials. We can do all sorts of basic operations to build up these equations. So for right now, let's just do a simple one. Let's just add 7. So now this becomes x plus 7. Now when I add 7 to this side, this scale is going to tip unless I do what? Unless I add 7 to the other side. 5 plus 7 is 12. So to keep that scale balanced, I have to do the exact same thing to both sides. And that is the governing rule to dealing with these equations, is whatever happens to one side, the exact same thing has to happen to the other side. So we just built a somewhat more complex equation here. Now, most of the time, we're not building equations. Most of the time, the command or the request we're going to be given is solve. When we're asked to solve an equation, what it's asking us to do is to take this equation back apart and get it back to this form here, x equals 5. Well, this equation was built by adding 7. So to take it apart, we have to do the opposite. What is the opposite of adding 7? Subtracting 7. So we subtract 7 here, that takes this piece off. Leaves us with x. Now again, because of that balanced scale, we have to do the exact same thing to both sides. So I subtract 7 over here, 12 minus 7 is 5. So I'm back to x equals 5. We've solved the equation. Now we built this equation, so we knew how it was built, so we knew exactly what we had to do to take it apart. So the first skill we need for equations is figuring out how they are built. So let's look at this one here. To figure out how an equation is built, the first thing we do, we find the equal sign. It's right there. Then we identify which side of the equal sign the variable's at. We find where the variable is. And then we ask ourselves, so there's 2 steps, one so far. 1, find the equal sign. 2, find where the variable is. 3, I'm going to split this into 2 parts. 1 is we're going to ask, what is keeping the variable from being alone? In other words, what's keeping the variable from being by itself on that side of the equation? Well, in this case, that would be the 9. So the second part of that is, what operation was used to build it on? So the 9 was attached to the y by what operation? It was subtracted, right? So now that that tells us how this equation was built. This equation was built by taking y and subtracting 9 from it. So to take it apart, what are we going to have to do? Add 9. 4 plus 9 is 13. So 13 equals y, or y equals 13. Now once we've got to this point, we can double check it. This is our answer here, 13 equals y, or y equals 13. But to double check it, we can go back to this original equation. And if y truly does equal 13, we can replace y with 13. So 4 equals, instead of y, we'll put in 13 minus 9. And if this is true, we'll get the same value on both sides. Well, the left side here is just 4. 13 minus 9 is 4. So we have the same value on both sides of the equation. So 13 equals y appears to be a correct answer. So we might have one like this. Here there's more than one thing happening. So we have to ask ourselves what's been done to the variable, to x in this case. Well, there's two things. We find our equal sign here. Here's our variable. There's two things keeping it from being alone, the 3 and the 2. The 3 is multiplied, and the 2 has been subtracted. Now, don't worry about solving the equation for right now. Let's just think about how it was built. Order of operations tells us if I have x, and I'm going to multiply it by something and subtract something from it, which one do I do first? Do I multiply first or do I subtract first? Well, order of operations says we multiply before we subtract, right? So this equation, when it was built, x was multiplied by 3 first. Then 2 was subtracted from it. You're just getting ahead of us to get to where we solve. When we go to solve this, to take it apart, think about, if you put something together, you're putting together a kit or a model or maybe a piece of furniture. You've just finished. You've just put on that last piece. And you need to take it back apart again. What's going to be the first piece you take off? The last piece you put on, right? Same with an equation. The last piece that was put on here to build it was subtracting 2. That's the first piece we're going to take off. So we're going to remove that minus 2 by doing what? Adding 2. So that minus 2 is gone, leaves us with just 3x. Again, we have to do the exact same thing the other side, so we add 2 to the 19 to make 21. And now what do we have to do? Divide by 3. Great. So x equals 7. So that form of equation like that is going to come up a lot. It's called a basic two-step form of an equation, where two things have been done to the variable. So here, x has been multiplied by 5, and then 3 has been added to it. What do we have to do to solve it? First thing we have to do to solve is subtract 3. So over here we have 45. Here we have just 5x. And then divide by 5. 9 equals x. Now just like we said before, we can always double check this. If this is true, I can replace this x with 9, and I'll have the same value on both sides of the equation. So 5 times 9 is 45, plus 3 is 48. So I do have the same value on each side. Okay, well, let's go one step further. So here, if we're going through our process, we find the equal sign. We're looking for our variable, and we see the variable occurs twice. We have 3x and 2x. But now if we're thinking about that balanced scale, both the 3x and the 2x are on the same side of the scale. So the question I'm going to pose for you is, can I take the 3x and the 2x and push them together into one big pile? Does that change the balance of our scale at all? No, they're on the same side already. So I can push the 3x and the 2x together to make 5x. I still have the negative 7. That doesn't change my equation at all. All I have done is simplified this side of the equation. On one side of an equation, I can simplify anything that needs to be, and it won't change the balance of that scale. In fact, I can simplify each side as long as I don't intermix the two. Of course, now that it's in this form here, what can we do? Add 7. So that's gone. 5x equals 30. And then divide by 5. Good. So x equals 6. Once again, we could go back and put 6 in for x and double check to make sure you get the same value on each side. At this point, I'm going to assume you guys can do that on your own and you can verify that's the correct answer. So slightly different from that one. Is this. So looking at this one, we have our equal sign, and once again we notice the variable appears twice, but this time it appears once on each side of the equation. So I can no longer just push them together to make a pile. So I have to get rid of one of them. And it's usually easiest to get rid of the smaller of the two. So I'm going to get rid of the 2x. Mathematically, we get rid of them by subtracting the 2x. So that's gone. All I have left here is 8. Now I have to remove 2x from the other side because I did it from this side. The only place I can take it from is the 5x. 5x minus 2x is 3x minus 13. So now I solve it by first step is adding 13. So 21 equals 3x. And then divide by 3. Good. 7 equals x. So there's one more level of difficulty we can throw into the mix, and that looks like this. Whenever we see parentheses, it should scream at us, do something here first. And there are two types of parentheses. One is that enclosing symbol. We saw that with our order of operations, and we had to do something inside that enclosing symbol first. This parentheses, there's nothing I can do inside of it, so it's not an enclosing symbol. The second is just a separator. It is just, in this case, it is just separating that number, 3x minus 1, from the rest of the problem. In that case, there's often something we can do to the parentheses, which is the case here. This parentheses can be multiplied by the 7. So, just like we were showing up above, we'll distribute. 7 times 3x is 21x, and 7 times negative 1, negative 7. And now we can solve this. What are we going to do? Add 7. So 21x equals 21, and then divide by 21. X equals 1. And at this point, I'm going to assume you guys can plug it back in to verify that's the correct answer. Well, let's have a little fun with these. So we've got 5 times the 3x plus 2 minus 2 times the 4x minus 5. Oh, what do I want to put in there? Equals 2 times 2x plus 1 minus 3x minus 7. Let's make it easy on ourselves. We'll go plus 41. So looking at this, it looks kind of ugly, but as long as we follow our steps, we're okay. Now, as I said before, when we're simplifying, we can work on one side of the equal sign at once, and then we can go to the other side. So we're going to do everything that we can on the left side here to simplify this first. So we see the parentheses. Nothing to do in this parentheses, so we're going to multiply by 5. I know we only got a couple minutes left, so I'm going to move through this one pretty quick. So 5 times 3x is 15x. 5 times 2 is 10. Now this parentheses, again, there's nothing to do in it, so we're going to have to do something to it. What is this parentheses being multiplied by? Yeah, it's not 2, it's negative 2. Good. Glad you caught that. So negative 2 times 4x is negative 8x. Negative 2 times 5 is a positive 10. Then we have the minus 5. So now we combine here. 15x and negative 8x is 7x. 10, 10, and negative 5 is a positive 15. So the left side simplifies to 7x plus 15. Now we're going to do the same over here. We have 2 times 2x is 4x. 2 times 1 is positive 2. This one's a little tricky. What are we distributing in this parentheses? A negative. We think of that as being a negative 1 times the parentheses. So negative 1 times 3x is negative 3x. Negative 1 times 7 is a positive 7. We still have the plus 41. So now we've got 4x and negative 3x is just x, or 1x. 2, 7, and 41 make 50. Is that right? Yep. So now we go ahead. We have to get rid of the x. So 7x minus x is 6x. Plus 15 is 50. We will subtract 15. 6x equals 35. And divide by 6. X equals 5.8333, or 5 and 5 6. Okay, so for Wednesday, your homework's going to be on page 49 through 50, 1 through 43, the odds. We didn't really get any time to talk about word problems, but we'll throw some of those in there later. Now I realize, let's see, which one is it? Is it Shawamigan? You guys are not in school on Monday. On Monday, what we're going to be talking about is mixture problems and some problem solving. Everybody else is out of school next Friday. So what will happen is next Friday, I'll lecture to you guys. I'll go through the problem solving and mixture problems with you guys. So by the end of next week, everybody back on the same page. You guys have a great weekend. Thank you.